Okay, so now we'll continue with this idea of counting. I guess maybe just a brief review. This section is about counting. So we think we all know how to count, but as you can see, there are different scenarios where you actually have to come up with an orderly way of figuring out how many things it is that you're actually counting. So we talked about a couple different possibilities of how to represent this. You can make a diagram, you can make a list. We did some examples with a tree. Make a chart. And now a list is nice because it lets you see quite literally every single possibility. However, of course, you certainly wouldn't always want to make a list. For example, the number of state license plates is over 17 million. You wouldn't want to have to write down every single one. So we came up with some simple formulas and arithmetic techniques of how to answer a question like that. So far all we have is, if you have a couple different possibilities, if there are multiple events, so to speak, and there are a certain number of possibilities for each one, then you just multiply. And that was the basic thing that we talked about so far. Next. Okay, so suppose you have 6 cans of paint of different colors and 4 walls to paint. How many ways are there to paint the room? Okay, and how'd you get 24? 4 walls times 6 cans. Okay. Does this cover every possibility? Why not? Or what are the different possibilities? We're only painting 4 walls. Exactly. So how many choices do you have to make? What's the one choice? Okay, so suppose you decide you're going to paint it different colors. Does that automatically determine how the room is going to be painted? No. So what's the first choice that you can make that actually tells you something about how the room will look? In a certain way, in a definitive way. What do you paint the first wall? And then after that, what do you have to decide? Okay. Why are there only 5 choices for the next? Because, I'm sorry? Why not? Why not? Does it say that the walls need to be painted all different colors? No, I didn't. I said there are 6 cans of paint of different colors, as opposed to 6 cans of the same color. Does it say that the walls have to be painted different colors? Okay. So how many possibilities are there for the first wall? How many possibilities are there for the second wall? Third wall? Fourth wall? 6, 6, 6, 6. And what do you do with those numbers? You multiply them. Think of each wall as an event. Alright. So this is very similar to the previous examples we had, like the getting dressed or the state license plate. This is really exactly the same thing. Now it's cloaked because it's asked in such a way that Rakib, it encourages you to answer 6 times 4. You're given the number 6, you're given the number 4, so why not multiply them? But that's not what's really going on in the problem. So one of the best things you can do in these counting problems is to ask yourself, how many events are there in this problem? Right? Like with the family problem, suppose a family has 3 kids, boy and girl, blah, blah, blah. How many events are there? There are 3 events. So whatever you do should have something 3 times in it. With the state license plate, there are 6 events, 3 letters and 3 numbers. So whatever you're doing, you should have 6 spots. Same thing here. 6 cans, 4 walls. You have to make a decision for each wall, so there are 4 events. So whatever you're doing should have 4 spots in it. And in this case, it's 6 times 6 times 6 times 6. Okay. So this is the first fundamental thing to understand about these counting problems. Okay. Next question. Suppose you have 5 balls you must put in 5 boxes. How many ways are there to do that?
Five times 4 times 3 times 2 times 1. Because you can't put the same ball in 2 boxes.
Right. So what's the first decision you need to make?
You put a ball in a box.
You put a ball in a box. Right. And how many ways are there to do that? 5. Next.
You got 4 balls left.
Yes. So the next thing is you have to put a ball in another box. Now how many ways are there to do that?
4.
Now there's 4. You dig? Sorry? Right. I guess it's I guess to make it clear, I should say each box must have a ball. Okay. So if each box has to have, so I've modified the question to make it more clear. So knowing that each box must have a ball, what does that tell you? Every box is going to have 1 ball in it. So once you put a ball in a box, for the next ball, how many choices are there? 1 less. Or in other words, 4. So there are 4 choices for the next ball. What about for the next ball? Right. You dig? Okay. So first of all, again, it's not 5 times 5, because then you're just taking numbers and multiplying without understanding what you're counting. That's the first thing. The second thing is it's not 5, 5, 5, 5, 5 for the reason we just discussed. Once you put a ball in a box, that box is no longer available, so now you have 1 fewer choices. Okay. So let's compare these 2 scenarios. In the first one with the painting, once you use a can of paint, it can be used again. Right, there's no reason it can't. In the second case, with the balls in the boxes, once you use a ball or once you use a box, it cannot be used again. It's done. So these 2 different scenarios. Oh, okay. So this is going to be 5 times 4 times 3 times 2 times 1. And that does work out to 120. And I should say the first one works out to 1296. Okay. So these 2 different sorts of scenarios have different names. The first one, where you can use the can of paint as many times as you like, that's called counting with replacement. The idea being that once you use the can of paint, it's not gone forever. You replace it back in your options. This one, where once you use a ball, it can't be used again, that's called counting without replacement. Once you use the ball, it's not replaced, it's gone. Okay. So this is another fundamental thing, aspect to understand about when you're trying to count, is whatever I'm using to make my possibilities, can I use it more than once? Okay. So here's an example. Suppose you have to visit 7 stores once each. In how many different orders can you visit the stores? Well, how many different events are there? There's 7 events. So how many choices are there for the first event? 7. And how many choices are there for the next event? 6. And then 5, 4, 3, 2, 1. And what do we do with these numbers? We multiply. Okay. So very nice. So does that make sense? Okay. By the way, this works out to 50, 40. Now, we have a short little notation for this. Writing down 7 times 6 did it all the way down to 1. That's called 7 factorial. What you write is 7 with an exclamation mark. So that's all that means. So notice that in the previous example with the balls, 5 times 4 times 3 times 2 times 1, what's another way that we could have written that down? 5 factorial, exactly. Okay, next. It actually, it's a notation for arithmetic. It doesn't. It can be used in these word problems, but it's a notation for arithmetic. 7 factorial just means 7 times 6 times 5 times 4 times 3 times 2 times 1. Starting with that number down to 1. All the integers, yes. Okay. Next. Suppose 8 horses run in a race. How many different top 3 finishes are possible? And for all you racing junkies, that's Win Place Show. Okay. So, first of all, how many events are there in this problem? Yeah, right, it's 3. Because how many we only care about the top 3 horses. We don't care about the others. So there are only 3 events. So, how many ways are there to do the first event? How many ways are there to do the second event? 5. Yes, there are 7. And how many ways are there to do the third event? 6. And what do we do with those numbers? Multiply. Okay. Does that make sense? Not sure? And okay, how many possibilities are there for the first place horse?
8. Because you only want 3.
Right. I only asked about the first 3, the top 3. So I only care about 3 events. But how many possibilities are there for the first event? There's 8 possibilities because there are 8 horses. Okay. So does that make sense?
So let's say it goes to
So
4. You would go up to 5.
then it'd be 8, 7, 6, 5. Okay. And this is 3, 3, wait, nope. Yeah, 3, 3, 6. Okay. Now, there's another notation for this one. Now, clearly this is not 8 factorial, because 8 factorial goes down to 1. So for this, we have a different notation. This is P. P stands for permutation. Okay. So actually, there's another notation. Okay. Oops. All right. So there are a couple different ways to write this. I'll usually write it the first way with little 8 big P little 3, but you can write it any of these ways and that's okay. So notice that this is sort of like writing out 8 factorial, but only writing out the first 3 numbers. Because again, in this case, we only care about the first 3 spots. What if, what's a larger number? Okay. Okay, so suppose you have to visit 15 stores once each, then what would the answer be? Suppose you have to visit 200 stores, what's the answer? 200 factorial.
So if you have
It's a very large number, but that's what it is.
So if you have like 20 stores, right? If you have like 20 stores.
It's, hold on one second. So it's not more complicated, it's just a bigger number. The answer is 200 factorial. Now I could say either leave it like that or tell me what the actual number is. But that's the answer. Okay, yeah, Terrell.
If you have like 20 stores, right? You have to write like, for the answer 20 times 19 times 8 is just like 20 factorial, that would be an answer.
20 factorial. Typically, I will give you numbers so you can actually calculate what it will be. 20 factorial winds up being quite large, so I'm probably not going to give you a problem where the answer is 20 factorial and you'd have to work it out. It's much bigger than that. Factorial gets very large very quickly. You'd be amazed. Yeah. So typically I'll give you numbers so that you can actually work out what the final answer is. But yeah, your first step should be to write down 20 factorial or 200 factorial or whatever, and then work it out from there.
And the number that's like in permutations, like the number that goes after permute is how many numbers you have to multiply down?
Yes.
So if it was 5, you would go 8, 7, 6, 5, 4, 6, 5, multiply.
Exactly. Right. So, yeah. So yeah, so to emphasize what Daniela said, if you're just given 8p3, for example, it means put 3 numbers. It does not mean go down to 3. That's a very big difference. So make sure you understand that. Yeah. That's next. Okay. So, and as a little bit of overlap, notice that 7 factorial is the same as 7p7. Well, 8p3 is 8 times 7 times 6. What would 7p7 be? 7 times 6. Right. Because it's the first 7 numbers, but the first 7 numbers just go straight from 7 to 1. With times. Yeah. Okay. Okay. So I'm such a big baseball fan, here's a baseball question. presuming, of course, that you know absolutely nothing about baseball. Okay. When a baseball manager makes a lineup, he has 14 hitters to put in the batting order, positions 1 through 9. How many ways are there to do that? Now, using notation, what's the really short answer to this question? 14p9. There you go. So notice that we're almost done. The only thing you need to do now is arithmetic. So 14p9 equals what in arithmetic? Okay. Tell me when to stop. Stop here. Stop here. Stop here. How many? How do I know when to stop? 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. Okay. And what do we do with these numbers? Multiply. Alright. So now you'd have to work out what that is. That's what calculators are for. And it turns out the answer is 726,485,760. I told you these numbers get very big very quickly. Yeah. That's a lot of options. That's why managers get paid the big bucks, right? Okay. I know. Okay. So, any questions so far? Let's see. Tyrell, any questions? No? Okay. So, in particular, before I go forward, I want to make a note, I want to, reiterate that notice how easy that last question was when you just thought about how can I represent this using notation and then sort everything else out after. Okay. Now, next. How many ways are there to select a committee of 3 from a group of 5? Let's say these 5 people are Yannick, Ruth, Valinda, Samantha, and DeWitt. Okay. So how many ways are there to select a committee of 3? What do you think? Okay. Okay. So initially, how many events are there in this problem? There's 3 events. Now, how many possibilities are there for the first event? Okay, well, what's an event? You have to pick someone for the committee. How many possibilities are there for the first pick? 5. How many possibilities for the second pick? 4. For the next pick? 3. Okay. So, if we were to do this naively, we would think that the answer is just 5 times 4 times 3, which is 5p3. And if you hadn't seen this topic before, that's what you would have said. Now, what's the problem? Well, let me give you some examples of some committees that we could pick. We could pick Yannick and Ruth and Valinda. That's one possibility. We could pick Yannick and Ruth and Samantha. That's another possibility. Or we could pick Samantha, Yannick, and Ruth. But what's the problem? The last two committees are the same. Why are they the same? They've got the same 3 people. Because what's different now in this problem that was not true before?
The order?
Yeah, what about the order?
It's different, but same people.
Right. So if the order is different, if the same people, but if the order is different, is it the same committee? Yeah. Now, is that true when you have a race? Right. When you have a race, does it matter what order the horses finish in? Absolutely. Okay. So having horse Good as Gold in the first spot and Moonraker in the second spot is very different from having Moonraker in the first spot and Good as Gold in the second spot. Those are 2 very different things in a race. When you choose a committee, do the same thing. You dig? Okay. So the thing is, simply writing down 5 times 4 times 3 assumes that we have a race, but here we don't. In this case, order does not matter. So this is a good start, but this is not the final answer. So what do we have to do? Well, how many times? So the thing is, we've counted committees that are the same. We've actually counted them as different. How many times have we counted each committee? Each same committee. For example, Yannick, Ruth, and Samantha. How many times are we going to count that committee? Well, we will only want to count it once, but how many times have we actually counted it? Well, the number of ways that we've actually counted it is the number of different ways that there are to write down the names. So if you've got 3 names, how many different ways are there to write it down that committee? Well, you've got 3 names, and you've got to put them in order. So how many ways are there to write down the first name? 3. How many choices for the second name? 2. And how many choices for the last name? 1. So there are 3 factorial, or 3 times 2 times 1, many different ways to write down this committee name. So this committee, sorry. So every single committee has been written, and 3 times 2 times 1 is 6. So every single committee has been written down using just writing it down naively this way. Every single committee has been written down 6 times. So what do we have to do with this answer? We have to not subtract. Divide, because every single committee has been written down 6 times. So in effect, what we've got is 6x, and we just want x. So we've got to divide by 3 times 2 times 1, or divide by 6. Okay. So this is a long way of saying that we need a new notation. Okay. So what marks off this scenario, what the distinguishing characteristic of this scenario is that order does not matter. And when order does not matter, you have to do what's called a combination. And we write this down as 5C3. Now I went through that whole big long explanation so you could see why there needed to be some kind of divide. When order does not matter, you counted committees extra, so you need to do some kind of dividing to adjust. Now, once we agreed that 5C3 represents the original 5 times 4 times 3 divided by what we need to divide by, now I'm going to give you a super easy way to think combination. So you can basically skip everything we just said. So you don't even have to think about it. Once you realize that order doesn't matter, you just write down 5C3. Now what's an easy way to write down 5C3? 5 factorial divided by 3 factorial and then 2 factorial. Where does the 2 come from? 2 plus 3 equals 5. So you might say, okay, great, you've given me something completely different to write down. What does that have to do with everything we just did? Well, is that the same thing? Let's take a look. Five factorial over 3 factorial times 2 factorial. Well, what do we have on top? 5 factorial is 5 times 4 times 3 times 2 times 1 divided by 3 factorial is 3 times 2 times 1 times 2 factorial, which is 2 times 1. And what happens? Cancel, 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 cancel. And what are we left with? 5 times 4 times 3 divided by 3 times 2 times 1, which is exactly what we want. So, (5c3) does all the work for you. So what winds up happening is all you really need to remember is when order does matter, I use P. When order does not matter, I use C. I'd like you to remember why, but if not, I guess that's okay. So let's put this in practice. So how many ways are there to select from 30 students, 6 of them to go on a trip? So? Okay. So this is going to be 30 something 6. So the thing we need to ask ourselves is what? Right. So does order matter? Going on a trip, does order matter? Nope. So 30c6. So at this point, the problem is essentially half done, but we do need to straighten. We do need to go ahead and do the arithmetic. So for 30c6, what's the arithmetic? How do we keep doing this? 30 factorial divided by 6 factorial. And then what else? 30 minus 6. And what number is what is 30 minus 6? Awesome. Because 6 plus what equals 30 is the same as asking what is 30 minus 6. Right? Yes. Okay. Now we got to straighten this out. Now how can we write this out? What's going to be on top? Times 27.
You can just go up to 24.
Okay.
After 24, it gets canceled out.
Right. 27, 26 times 25.
That's it. Times 24.
And then what happens? Do I need a 24 here?
Oh, no, it's just one I canceled out.
Exactly. So everything after everything starting with 24 is going to cancel with the 24 factorial. You get it? Okay. So, and just to make that clear, I'm going to write times 24 factorial, and then in the bottom 6 times 5 times 4 times 3 times 2 times 1, and then times 24 factorial. But now all that other junk will just cancel. So obviously save yourself some work, cancel the bigger ones so you got less stuff to deal with. Does that make sense? Okay. So now you just have to use your calculator on the remaining couple numbers, and that should be pretty straightforward. You wind up getting 593,775.
Can you divide those little numbers, the bigger numbers into little numbers?
Absolutely.
Yeah,
Sorry?
like 630, 328, 226.
Yeah, I mean, if it makes you happy, you can certainly give yourself less work to do on the calculator. 6 times 5 is 30, so that cancels with 30. So if you want to do that, you can certainly go ahead and do that. So, boom, boom, boom. 3 goes into 27, 4 goes into 28. You can certainly do all those things. Okay, next. How many ways can you select from 30 baseball teams, 8 to go to the playoffs? Okay. So what's the question we need to ask ourselves? Does order matter? The way that I've asked this question, does order matter? It's just saying there are going to be 8 teams in the playoffs. So 30C8. And then of course we need to work that out. 30 factorial over 8 factorial, 22 factorial. 30, 29, 28, 27, 26, 25, 24, 23, and then everything else I can just say is 22 factorial. 8, 7, 6, 5, 4, 3, 2, 1. And then how nice for us, the 22 factorials just cancel. And then you can just use a calculator to work that out. Now a tip, what Terrell said is actually really important, because sometimes if you just try to multiply all the numbers on top directly, that number will be too big for your calculator. So sometimes it is actually necessary to divide along the way instead of just multiplying all the numbers first. Does that make sense? Okay. Okay. How many 4-digit lottery numbers are there? Four P what? Okay, so 4 factorial. Is this the right thing? So 4 times 3 times 2 times 1. What is a 4-digit lottery number? Give me one possibility. Yeah. So how many possibilities are there for the first digit? 10. So we've got 10 possibilities. 0 through 9. There are 10 different digits. Okay, so, sorry? 4p10.
I know it's 10 times 10 times 10 times 10.
Yes. Okay. So the important thing here is that once you use a digit, you can reuse it. So presumably everyone knows that about like pick 4 or whatever lottery numbers. You can have 2222. That's a lottery number. So the thing is that this is not permutation or combination because you can reuse stuff. So this just goes back to how many ways are there to paint the walls. So for this, you have 4 slots to fill, and for each slot, how many possibilities are there? 10, 10, 10, and 10. So this is just 10,000. Okay. Sorry? That's a good question. Okay. So typically the interpretation is if you're talking just about lottery numbers, you can have a 0 in the first spot. Okay. Now, if someone said how many 4-digit numbers are there, then we don't consider a 0 in the first spot to be a 4-digit number. But the lottery is just a lottery. So I'll just say that I will be flexible in grading if you were to interpret it that way. I'd probably accept that. Because that's a pretty clever thing to say. And in some cases it's right, so I'd probably just let it go. Okay. But so the thing that I wanted to bring out was that remember that this was actually the first method of counting that we learned. You've got a certain number, we've got 4 different events, certain number of possibilities for each one. So you just do, in this case, 10 times 10 times 10 times 10. So I want to remind you of the simple way of doing things. Exactly. 10 to the 4th. So in our decision process, the first thing you need to ask yourself is, can I reuse these things? And if you can reuse these things, then it's just the same number multiplied by itself a couple times. Or, if you can't reuse them, then you need to say, then you're going to have a permutation or combination. And you have a permutation when order matters, and it's a combination when order does not matter.
But I think it is
So why don't you guys do these last 2 poems? So let's talk about these, and let's talk at least about how to set them up. So, for the first one, how many ways can you elect 5 out of 20 soldiers to go fight? Yeah. So, yeah. Now, why is it 20c5? Right. Order does not matter. And then you can work out whatever this is. So this is going to be 20, 19, 18, 17, 16 times 15 factorial divided by 5 times 4 times 3 times 2 times 1 times 15 factorial, and those are going to cancel. And then you just need to work that out. Blah, blah, blah. Okay. Next. How many 4-digit lottery numbers are there in base 6? And how'd you get that? Okay. 6, 6, 6, 6. And what does that work out to? Oh, you're off by a factor. 1296. So notice that in this case you can actually simply say I have 4 events, and I can identify how many possibilities there are for each event, so I can just multiply. Notice that you don't want to do that for the previous problem. Well, you could do it that way, but then you also have to divide out, is what winds up happening. But the easier way to do it is just to recognize that you've got a situation where you're choosing things and order does not matter, so it's 20C5. So in this case, diagnosing the problem is the first step, and it's the most important step. Because once you do that, the problem is half done. Okay. Any questions about what we've done so far? The which one?
Yeah.
Base 6. Okay. Well, what do we know about base 6? Who? Oh, Hugo, or someone said it. How many? Yeah, you have 0 through 5. So how many different digits are there? There are 6 different digits. So now, how many events are there? There's 4 events. How many possibilities for the first event? It can be one of the digits. So how many possibilities are there? 6. And then for the next one? 6. Okay. So yes? Okay. Okay. So, right. Okay. All right. So let's. So I want you guys to help me do these. How many ways can you elect a colonel and sergeant from 9 candidates? Okay, so you said 9P2, 9C2, so which one is it? Why?
No, actually it's going to be 9C2 and 9P2. 8P2. 8P1. No. Wait, hold on. It's going to be 9C2.
Okay, why?
They don't tell you if it has to be followed. Like, it doesn't matter.
What doesn't matter?
They're just asking you to just do positions.
Uh-huh.
So there's no, like, an order that you have to follow.
Okay. Does it matter?
So
What if I said...
Each person can be either a colonel or a sergeant.
Right. Now, if instead of colonel and sergeant, I said first place and second place. But what's the difference? There's no difference.
I feel like
Let's put it this way. If you have 2 slots to fill, what do we call those? What do we call these 2 slots? Colonel and sergeant. Does it matter which person you put in which spot?
Yeah.
Stars and bars, it sure does matter. So how many possibilities are there for the colonel? And how many possibilities are there for the sergeant? And can you switch them around? Yes. And then you would still get 9 times 8 and it would still give you 72. So that would be the equivalent of labeling one position second place and then labeling the next one first place. Okay, but notice that the arithmetic winds up being the same if you did sergeant then colonel. Okay. So notice that order doesn't literally mean first, second, and third. Order means that you've got, in a more abstract mathematical way, order means you've got each spot labeled and you can't switch and they're not interchangeable. Really, that's what it means, that they're not interchangeable. So colonel and sergeant, are those interchangeable? No. But if you have a committee, are the positions interchangeable? Yes. Right. So if you're sending 5 soldiers to fight, are the positions of the soldiers interchangeable? Yes. You're still sending the same 5 soldiers. Okay. So to be really precise, to understand what this means, it's not really about order 1, 2, 3, 4, 5 per se, it's about interchangeability. Next, how many ways are there to select 5 starting pitchers from 11 pitchers? Okay, so Shaquille, why? Why is it? You're telling me 11 C5. Why is that? That's true. You use no pitcher more than once. And so that's the first thing. And then the second thing we need to figure out is what? Right. Does order matter? Rian says no. So what do you think? The way that this question is asked, does order matter? Why? Because, sorry? Every single question will start with how many ways. But does order matter? No. The way this question is asked, order does not matter. It doesn't say anything about the pitchers being in order. So, and there's no reason to think they need to be in some particular order, so order does not matter. So, I'm going to need this, so let's work this out. This is going to be 11, 10, 9, 8, 7, 6, actually, times 6 factorial, over 5, 4, 3, 2, 1, times 6 factorial. Those cancel, and now I want to work out what this is. So, let me work that out. Okay. So this is equals 11 times 10 times 9 times 8 times 7 divided by 5 times 4 times 3 times 2 times 1. Whoa. Nope. Times 1. Okay. That gives 462. There you go. Okay. So, with or without replacement, order matters, order doesn't matter. Those are some of the central questions you need to answer. when doing these counting problems. Okay, so we just did a bunch of examples. Any questions on these examples? Anything you want to revisit? Tracy? No? Daniela, you're always good for a couple questions. Any questions?
The only one you left me maybe confused was the one in the column and
But, yeah, okay.
like, I understand when you explain it, it makes sense, but if I saw it, I wouldn't have that approach.
Okay. So the important thing to remember is that order really means, what does order matter or not is really what it's asking is, are they interchangeable? So are colonel and sergeant interchangeable? If you call one guy colonel and one guy sergeant, if you switch them around and call one guy, the first guy sergeant, the second guy colonel, is that different? Yeah, that's different. So that's the same as saying order matters. And so that's simply different from previous problems. Which students go on a trip? Does it matter which order they go on a trip? No. So once you've chosen 6 to go on a trip, those 6 are interchangeable. So that's the difference. Okay. So any other questions on these problems? Edgar, any questions? No. Okay. So now we're going to kick it up a notch. One hopefully simple notch. So you notice I asked two different baseball questions. The first one I said is, how many ways are there to make a batting order? And then I said, how many ways are there to select 5 starting pitchers? So now managers actually have to do both of these things. You've got a roster with 14 hitters and 11 pitchers. First of all, you have to make a batting order, and you also have to select your starting pitchers. So how many ways are there for a manager to do both of these things?
Can you do them separately?
Yes.
Yeah.
Right. But didn't we already do that? Yeah. So, how many ways are there to make a batting order? It was something million. Where was it? There we go. Okay. 726,485,760. See if I can remember that.
It's out of 11 players, right? 11.
Yeah, it's the make a batting order, same problem, and then select starting pitchers, same problem. It's, in other words, make a batting order, that's just shorthand for what I previously asked. How many ways? If you have 14 hitters, you have to make a batting order 1 through 9.
Wouldn't it be both combination and permutation?
Okay. So how would this look?
Well, the first one to make a batting order would be combination, and then the second one to select starting pitchers. You already chose like 5 pitchers or something, so that means you only have 6 players left.
No. We're starting from scratch. We're not assuming that I've already done anything. We're just basically what I'm doing is we're cheating because I'm saying we've already done little parts of this problem. Well, okay. So here's the question: how many ways are there to make a batting order? In other words, 14 batters from 14 hitters, select positions 1 through 9.
Mm-hmm.
And then, how many ways are there to select starting pitchers? In other words, from 11 pitchers, choose 5 for your rotation. So what do? Well, how many ways are there to make a batting order? We know that was 14P9, which is this big number. Now, how many ways are there to select starting pitchers? We know that's 11C5, and we know that's 462. Now, what do you do with those two numbers?
Then I have to completely different things. I have to use combine.
What do you do with these two numbers? This is just shirts and pants. Four different shirts, 3 different pairs of pants. How many outfits? 12. 726 million batting orders, 462 starting pitchers. What do? Multiply. Does everybody see why it's exactly the same thing? Because what do you have to do? You have to pair a batting order with what's called the starting rotation. Now, what's tricky about this problem is that I don't just, to start the problem, I wouldn't just tell you, I'm not telling you how many different batting orders there are, I'm not telling you how many different starting rotations there are. You have to separately figure that out. So this is harder than if I said you have 4 different shirts and 3 different pairs of pants. How many outfits are there? But it would be exactly the same question if I said there are 726 million batting orders and there are 462 starting rotations. How many different teams can the manager put on the field? Does that make a bit of sense? Because selecting a shirt and selecting a pair of pants is, in this problem, the same as selecting a batting order and selecting a starting rotation. What's harder is you have to figure out what each number is first. This is going to be a huge number. So this winds up being 726, 485, 760 times 462. Whatever that is. Did I do that right? Okay. So there's over 335 billion possibilities. All right. So like I said, these numbers get very large very fast. All right. So let's work out this one. Slightly different. The numbers are a little, actually, we won't actually figure out the numbers. Let's just figure out how to set this up in notation. For your work schedule, you need to select 21 days in January and 23 days in February to work. How many ways are there to do this? So what's the first thing you need to do? Select 21 days in January. Now, how many ways are there to do that? $31 days in January, 28 days in February. So you have to do January, and then what's the other thing you have to do? February. And when you have those numbers, what are you going to do with them? You're going to multiply. Now, how many ways are there to choose which days you're going to work in January? The bigger number has to be first, because it's out of this many, choose this many. So out of 31, C21. And then what about for February? Okay. Absolutely. So the problem is now almost done, and I'll leave you to do the arithmetic. So I think the hardest thing to understand is why Rakib is right, and that this should be C for combination. So does order matter? Why not? Okay. So imagine that you have the calendar of January in front of you. So 1, 2, 3, blah, 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 29, 30, 31. Basically what you've got to do is what? You've got to circle 21 of those days. So suppose that you circle, and let's just make it easier, let's say 1, then 3, then 29, and a bunch of other stuff. Does it matter the order that you've circled the numbers in? If you circle 1 then 3, or you circle 3 then 1, does that matter? No. Okay. So this can be a little tricky to understand, but the argument of why order does not matter basically boils down to that. Is that it doesn't matter which order, it doesn't matter the order in which you pick the days, but those are your days. Once you have the days in which you're working, you can't rearrange them. You're not going to work on the 3rd before you work on the 1st. Okay. So I understand that might be a little hard to see why that works, but hopefully if you think about it, you can master it, and that's the final idea for this topic. Understanding why order doesn't matter in a case like this. Okay, so the last thing we looked at were these tricky, what I call these compound events, very compound, where you need to figure out you need to individually figure out how many ways there are to do a couple different tasks, and then you multiply them together in your last step. So notice, for example, for your work scheduling, just like 21 days in January and 23 days in February. If you weren't thinking, probably what would you do in order to answer this question? 21 times 23. But notice how that's completely way wrong. Because the question you need to ask is, how many different ways can I select 21 days in January? And that's a separate question. Then, how many ways can I select 23 days in February? And that's a separate question. And then, since you need to do both, it's like shirts and pants, and you multiply. Right. So I think this is probably the most elaborate sort of question in this section, simply because it has problems within the problem. Okay. Next, let's see. So now I said most elaborate, but I don't think it's the hardest problem. So I'm now going to talk about what I think is probably the hardest sort of problem in this section. Okay. Which I'll get to shortly. Suppose you have a string of 3 lights which can be on or off. How many possibilities are there? Well, how many events are there? There's 3 events. How many possibilities for the first event? Second event? Third event? And what do you do with those numbers? Okay. So you get 2, 2, 2, and you multiply, and that gives you... What's 2 times 2 times 2? 8. Okay. So this one is straightforward. Because what are the possibilities?
On and off.
On and off. Okay. Here's the tricky problem. How many possibilities are there if you cannot have 2 consecutive lights off? So I will tell you directly, this is a hard problem. I don't think so, but let's check it out. Alright. So the way to work this out is with a tree. I'll tell you that directly. So notice that we're going to have a tree where we've got first light, second light, and third light. Okay. Now, what are the possibilities for the first light? On and off. Okay. So far, so good. Now, what are the possibilities for the second light? It depends. If the first light is on, what can the second light be? It can be on and it can be off. Now if the first light is off, what can the second light be? It can only be on, it can't be off. You dig? Because what is the restriction that the problem says? You cannot have 2 consecutive lights that are off. So if the first light is off, what does the second light have to be? It has to be on. Okay. So now we go to the third light. So notice that in the first case we've got on. What can the third light be? It can be on or off. Now, in the next case, what could the third light be? Can it be off? It cannot be off. Okay. And for the next one, what are the possibilities for the third light? It can be on. Can it be off? If the second light is on, can the third light be off? Yes.
Like we're doing it like this. You have to apply.
So remember, read this across. So what does this say? This last combination on the tree is off, on, off. Is that acceptable? Yes, because what does it say? You cannot have 2 consecutive lights off. Not 2 total, 2 consecutive. You understand? So, finally, how many total possibilities are there? Five. Right? 1, 2, 3, 4, 5. What's the first possibility? Instead of on and off, I'm going to put yes and no so I can just use one letter. First possibility is yes, yes, yes. And what's the next one? Yeah, Yes, yes, no. And then yes, no, yes. And then no, yes, yes. And no, yes, no. So those are the possibilities. So there are 5. Alright. So why is this problem hard? this problem is hard because the number of possibilities you have at each step changes. How many possibilities are there for the second light bulb? Well, it could be 1 or it could be 2. It depends on what the first light bulb was. So notice that we can't write this out as 2 times 2 times 2 because there are not always 2 possibilities for the second bulb. Does that make sense? Alright. So because this is so complicated, because the number of possibilities changes, you have to do a tree. You could do a list, but I think it's better to do a tree because it makes sure that you do every possibility, or at least make a tree and then make a list from the tree. Okay. So how do you know when you have one of these difficult sorts of problems? We can't notice that we'd much rather just be able to do something with arithmetic, like 2 times 3 or 5c4 or whatever. But how do you know when you have a problem when you can't do that? In other words, one of these problems. Sorry? Yes, but how do you know when the... Right, so you'll use a tree to solve the question, but how do you know when you have such a question? Yes. When you have when the number of possibilities changes. Right? So in general, how many possibilities are there for a light bulb? 2. But will it always be 2? No. It depends. So that's what makes this a tricky problem, and that means you have to do this, get your hands dirty and do a tree. So this is a rather, again, tricky sort of problem. I'd like to see if you can handle it. I think you can. Okay. So 2 more things. First of all, another note about trees. We've sort of talked about this before, but we've talked about this indirectly before. Drawing a tree, and again, I'm going to pull back from these tricky trees. I'm going to go back to just making regular trees. So regular trees are drawing a regular tree is just like making a subset. What? How do I mean that? Well, you can use a tree to make a subset in the following way. So for example, we talked about, actually the very first day we talked about Paul having toys and Jimmy having toys, and we talked about one set of toys being a subset of the other set of toys. You guys remember day 1? Yeah. Okay. So, what does it mean to make a subset? Well, what it means to make a subset, in one sense, is you go through every single toy and you say either it's included or it's not included. So, you can represent that using a tree. So for example, suppose you have a set of toys, doll, truck, scooter, ball. How do you make a subset? Well, first of all, let's name me one subset of this set of toys. What would one subset be? Doll. Okay. I'm sorry? Doll. Okay. Right. Doll is a subset. Well, one way to do that is just to say I'm going to take a bunch of them and that's a subset. Another way to do this, to think of it in terms of a tree, is to say Well, for dal, I need to decide, is it going to be included in my subset or not? Then you go to truck and you say, is truck going to be included in my subset or not? Same thing for scooter, same thing for ball. So when you make a subset, in effect what you're doing is making 4 different decisions. And each of those decisions has 2 possibilities. Yes or no, include or not include. Does that make sense? Okay. So how can we draw this as a tree? Well, we've got 4 different decisions, so the tree has 4 different stages. So first we do dal. So, and if you remember way back to set notation, you put a bar over something to represent the opposite. Okay. So the first thing you've got is you've got 2 choices, dal or not dal. And then once you've chosen dal or not dal, you've come to truck, you've got 2 choices, truck or not truck. And then after that you've got 2 choices, scooter or not scooter. And then after that you've got 2 choices, ball or not ball. And then the way that you do a tree is every time you have a choice, you need to branch off of that one. So dal branches twice into truck and not truck, and not dal would also do the same. I haven't finished the tree. I've just done the top half of the tree. So then you also, off of truck, you have scooter and not scooter. And then off of don't include truck, you have include scooter and not include scooter. So how can we interpret this so that this gives us all the subsets? Well, the top branch up here, what subset does that indicate? You've got D, T, S, B. So what's that subset? Exactly. It's the subset is actually the same thing you started with. Now what about the next one? What subset does that indicate? Right. Dal, truck, scooter, not ball, so just dal, truck, scooter. Now what about this one? What subset does that indicate? Dal, truck, and ball. And then what does the next one indicate? Dal and truck. And that's it. Okay. So does that make sense? Okay. So notice what's nice about this is that it gives you an organized way of writing down every single subset. It makes sure that you include every single possibility, instead of just trying to name them off the top of your head. Okay. So that's the first thing. The second thing is this also gives you an idea of how to count the number of subsets. So setting it up like this, how many events are there? How many stages in your tree are there? There's 4. 1 for each original element. Now how many possibilities are there for each event or for each step? There's 2. So how many different subsets can you possibly have? 2 times 2 times 2 times 2. And what's another way to write that? 2 to the 4th. So if you recall, what we originally said is that n objects has 2 to the n subsets. If you think back to week 1 or whatever it was. Well, now we've in a sense proved that. We've shown why this is true. Instead of just doing a couple different examples and me giving you a formula, we've actually shown why this is true. Every additional object gives you 2 more possibilities, and you have to multiply by 2. Or I should say, gives you a choice gives you an option with 2 choices. So that's why you multiply by 2. Okay. So that's just a little bit of a first day, last day tie together. Okay.